with Bob, Dan, and Giovani, which turned into my master thesis, which I had to submit this morning. So the slides are going to be mainly copy and paste from the thesis. So basically, the aim of the paper was to try and introduce a fragment of natural language which would be used as a mid-level representation between full-blown natural language on one side and machine language on the other. So it's trying to connect all the work that's been done previously in Coecke models of meaning, modeling complex phenomena like relative pronouns, to, on the other side, well, database theory and basically knowledge graph natural language questions as knowledge graph queries. So the general idea of this Coecke model is that you take an utterance, so a sequence of natural language words, and you take the tensor of those words together, you encode the words, and then you are going to compute similarity between the words that you've computed based on the grammar of the sentence. And that gives you a scalar which you interpret as a generalized truth value for the sentence. So the first step in our paper was to, graphically the intuition was usually in strict diagrams for monoidal categories. The intuition is that time flows vertically in the sense that you have composition of arrows meaning processes in sequence, whereas tensor of arrows meaning processes in parallel. Here, well, time seems to flow from left to right because that's the way we write natural language. So the idea is if time flows from left to right, then well, from bottom to top, it should actually be space. So in this particular case, basically the number of underlinks you have at the bottom, the number of cups that you have for the grammatical reduction for your sentence is going to bound how many vectors you have to keep in memory. So the height of the picture is going to be space, the length is going to be, from left to right is going to be time. So the idea is that if you compute this diagram, so if you take from top to bottom the utterance, then the encoding for that utterance, then the grammatical reduction, you get the meaning of the sentence, but you also get a way of computing the answer for the corresponding yes-no question. So Alice loves boys that tell jokes is true if does Alice loves boys that tell jokes, the answer to that question is yes. So next step is where do we get the answers from? So the idea is we're going to use the resource description framework, which is the standard for the semantic web. So we're going to encode our knowledge in a knowledge graph, which is a set of entities which the nouns refer to, a set of relations which the verb refer to, and a subset of those which we consider as true. So in that particular case, we only focus on transitive verb. So we're going to take love as a universal example. And we're going to use one hot encoding to denote every entity with a vector with one bit up, every relation in a similar way. So then the key intuition is that an effect, so a column vector actually corresponds to a knowledge graph query. So the most basic query you obtain by just summing over all the triples that are in the knowledge graph. You get an atomic query for membership of one triple, and that allows you to, in a way, open the box for the verb relation and say that the meaning of a verb is given by the sum over the encoded meanings for the entities that it relates, which is very similar to the ideas that Paul Smolensky discussed earlier this afternoon. So once you've opened the relation box, or the box for verbs, you can start you can start looking at more complex sentence structures and basically read those equalities, which, well, you start from the observation, which comes from Frobenius anatomy paper from Manouche et al. Manouche Sazrade et al. That Frobenius algebra was allowed to model definitions. So the idea is you want to take those pairs of a word together with its definition as constraints that you add onto your encoding. So in a sense, they could be seen as constraints of the encoding matrix, the encoding matrix E. They could be seen as examples that you feed your machine so that it computes the matrix E. So you can ask for equality, you could ask for point-wise order in the category MAT-S. You can also do mixtures to model disjunction. So now, modeling yes-no questions will prove to be pretty hard because you need a good model for the word not, which seems to be pretty elusive. So we focused on object questions instead. So the idea is the set of answers for an object question is going to be the set of entities for which the corresponding sentence is true. So here we write the diagram for the question with who as an open wire, and we get an effect from the cardinality of the entities to 1, which means that every time we take an entity, we can take its scalar product with the effect, or we can take the composition with the effect and get a value. So we can rank our entities and pick the one with the highest value according to this question. So depending on the truth value S that we choose, we're going to get different answers. So we could get a Boolean answer which recovers Montague's semantics framework. If we take S to be the Booleans, we could take non-negative probabilities, non-negative reals to encode probabilities. We could take min and max of the unit interval to model fuzzy logic. So basically, it's all parameterized on this set of scalar S, which encodes what we take to be truth value. So now we can build more complex queries by using the definition idea from 2 slides before. By symmetry, we can model subject questions as well as object questions. So we get to examples like who loves boys, that tell jokes. So if the scalar from the first slide was true, we should have that Alice is an answer to this question. So a next step could be to open 2 wires and make a question of 2 arguments. But instead we went into defining a class of a fragment of natural language which allowed to recover the effects that we got from the questions before, as well as a large class of effects for any arbitrary number of arguments. So it starts with the idea that a personal pronoun as well as a question word should be an open wire, in the sense that in order to compute the meaning of one of these 2 sentences, we need to know what him or he refers to. So it needs some context. Where we get this context from is going to be a notion of memory, which is what we're trying to model here. So the idea is if we take directly this, if we take this diagram as an effect directly and we compute the argmax of the pairs him and he, we're going to get counterintuitive results like Spinoza influenced Wittgenstein, Newton discovered calculus, which in that particular context doesn't make sense because a natural language speaker would assume the him and the he to refer to the same entity. So in order to encode those types of natural language constraints, we use discourse representation structures, which were introduced in the late 70s in order to model these constraints. And it gives us a framework for probabilistic anaphora resolution in the sense of Abramsky and Sartre. So the idea is we have a set. So if our sequence of sentences has n or has k anaphoras in it, we need to map every one of those k's to an entity, and not all of those mappings respect the constraints. We have a subset of these matching functions that respect the constraints, and we want to take the argmax over those. So once we have found our argmax, we have resolved the ambiguity in the discourse in the sense that every entity is assigned, every anaphoric noun, subject, or object is assigned an entity. So the way we actually show the memory mechanism, or the way our model uses memory in that particular case, is by building what we call an entity store, which is basically taking the tensor of all the one-hot encodings for all the vectors. So it has a really big dimension, or an exponential dimension, but all the vectors in here are one-hot vectors, so it's a very sparse state. And the idea is more to get an abstract picture overall than to actually explicitly represent this state in memory. But once we have this entity store, we can build from the matching function a process which takes this store and retrieves the vectors from memory. So in this particular case, let's say the entities we know about are Descartes, Spinoza, Leibniz, Newton, and calculus, and we take the discourse just before, so the sequence of sentences just before, and we decide to map Leibniz to both him and he. What we get is what we call the resolved discourse. So the idea is it's the composition of an entity store followed by a matching function which feeds the information from the entity store into a discourse. So the idea is to try and separate on the bottom the dense computation, which involves word vectors which encoding similarity, from the, let's say, symbolic sparse representations on top where all the vectors are one-hot. So here we managed to separate, so in the box R as well, you have this separation of the knowledge graph K being a dense matrix, whereas the knowledge graph K being a sparse matrix, whereas the encoding matrices E are all dense. So once you get this picture, you have symbolic reasoning on one side on the top, you have dense reasoning on the bottom, statistical reasoning on the bottom, and time flowing from left to right. The only thing missing is that we've sort of had to fix an ordering for the entity store and write it in a line, and now we lose the intuition that time should go left to right, because here we really want the memory to go, let's say, on top. So we really want a notion of a stack of vectors that we can remember. How am I doing on time?
You've got just over 5 minutes.
Okay, good, so I wrap up.
7 minutes.
So the general idea is we want to take a large corpus of natural language data. We want to translate it into this mid-level representation where it's still quite close to machine format, but there has been work already to translate natural language into this format. And from these diagrams, basically compute constraints on the encoding matrix E, in the sense that every time you have an utterance, every time you have a discourse of this shape, you can use it as training data for your encoding matrix. So in the future work, there's implementing the examples with large scale, or implementing this with large scale examples using semantic web data, RDF being a good standard for that, in the sense that we have a lot of nice data sets to work with. And implementing questions as Sparkle queries, which is the standard language for knowledge graph queries over the semantic web. Then there's one other branch of another potential direction would be looking at implementations using more modern machine learning techniques, like the tensor product representations that, of course, Melansky was talking about, and another approach with knowledge graph completion, which would allow to get the encoding matrices with the properties we desire by construction. Then another direction would be to try and formalize the matching process properly, categorically. Another one would be to try and integrate what we've done together with the work on generalized quantifiers, which would be really helpful in that context, so that we could express quantified queries over knowledge graphs. And finally, looking at props, so products and permutations categories, as a tool to find a mapping, to build neural networks that would build neural networks architectures directly from the syntax of natural language in a functorial way, trying to build up on the work from Fong, Spivak, and Torres from last year. So, yep, that would be all for me.